Assalamualaikum and good day to everyone. Okay, today I will teach you on chapter 3, which is a DC machine drive. Okay, in this chapter, I will give a brief introduction about the DC machine, and then we will learn how to start the DC motor, and then how to control the speed and how to brake the DC motor. Okay, as you know, in DC machine we have a two type, which is a DC motor and DC generator. But in this topic, we just cover on a DC motor. Okay, a DC motor is any of a class of rotary electrical motors that converts direct current electrical energy into mechanical energy. And the most common types rely on the forces produced by magnetic field. Okay, DC motors are categorized in a number of types based on the input supply, construction, and principle of operation. Mainly, there are two types of DC motor. Okay, first one is separately excited DC motor and self-excited DC motor. And then the self-excited motors are further classified as shunt DC motor, compound DC motor, and series DC motor. DC drives are widely used in applications requiring adjustable speed, good speed regulation, and frequent starting, braking, and reversing. And some important applications are rolling mills, paper mills, mine windows, hoists, machine tools, traction, printing presses, textiles mills, excavators, and cranes. And fractional horsepower DC motors are widely used as servo motors for positioning and tracking. Okay, although since late 60s, it is being predicted that AC drive will replace DC drive. However, even today, the variable speed applications are dominated by DC drive because of low cost, reliability, and simple control. Okay, next, the DC motor comprises four principal components. The basic working principle of a DC motor is whenever a current carrying conductor is placed in magnetic field, it experiences a mechanical force. And when armature windings are connected to a DC supply and electric current setups in the windings. So, in this figure, you can see the four components of DC motor is field, armature, commutator, and brushes. Okay, as I mentioned before, when armature windings are connected to a DC supply and electric current setups in the winding, magnetic field may be provided by field winding or by using permanent magnet. We have a permanent magnet here. And in this case, current carrying armature conductors experience a force due to the magnetic field according to the principles stated above. Okay, and then we have a conductor here. Conductor here carry a armature current. And then commutator is made segmented to achieve unidirectional torque. Okay, otherwise the direction of force would have reversed every time when the direction of movement of conductor is reversed. in the magnetic field. This is how a DC motor works. Okay? And according to the fundamental laws of nature, no energy conversion is possible until there is something to oppose the conversion. Okay, in case of generators, this opposition is provided by magnetic drag. But in case of DC motors, there is back EMF here. Okay, and then when the armature of a motor is rotating, the conductors are also cutting the magnetic flux lines, and hence, according to the Faraday's law of electromagnetic induction, an EMF induced in the armature conductor here. Okay, and then the direction of this induced EMF is such that it opposes the armature current. Okay, armature current will flow here, and then we have a flux from north to south. Okay, as we know, energy neither can be created nor it can be destroyed. It can only be transferred from one form to another. And in DC motor, electrical energy is converted into the mechanical energy. And then during this process, the total input power is not transformed into output power. Some parts of input power gets wasted in various forms. The form of this loss may vary from one machine to another. These losses give in the rise in temperature of the motor and reduce the efficiency of the motor. This is somewhat you feel that your motor is getting hot. Okay, and in DC motor there are broadly 4 main categories of energy loss. Okay, the first one is electrical losses or copper losses, or we can call it a winding losses. Okay, the copper losses are the winding losses taking place during the current flowing through the winding, armature and field winding. And these losses occur due to the resistance in the winding. Means that we represent the winding as a resistor. And in a DC machine, there are only 2 windings, armature and field winding. Thus, copper losses categories in 3 parts: armature loss, the field winding loss, and brush contact resistance loss. The copper losses are proportional to the square of the current flowing through the winding. Okay, and then we have a mechanical losses. Okay, the losses associated with mechanical friction of the machine are called mechanical losses. These losses occur due to friction in the moving parts of the machine like bearing, brushes, and windage losses occur due to the air inside the rotating coil of the machine. And these losses are usually very small, about 15% of full load loss. And then we have core losses, or we can call it iron losses, or we can call it magnetic losses. Okay, as iron core of the armature is rotating in magnetic field, some losses occurs in the core, which is called core losses. Normally, machines are operated with constant speed, so these losses are almost constant. And these losses are categorized into form, which is hysteresis loss and eddy current loss. Okay, please find by yourself what is the hysteresis loss and what is the eddy current loss. Okay. Okay, next we proceed to the wiring topologies of DC motor. Okay, from here we can identify what types of DC motor it is. Okay. Okay, first, okay, the armature circuit is represented by an ideal voltage source EA. Okay, if you look at the figure A, B, C, and D, we have a EA. This is represent the armature circuits. Okay, and then we have a RA. It's also represent the armature circuit. VT is the terminal voltage or line voltage, and RF represent the field winding. Okay, and here we also have a I line. Okay, I line and IF, which is the field current. Okay, figure A is shunt DC motor. Why? Because the armature and field is connected in series. Okay, figure B is separately excited DC motor, where the field winding and armature winding is separate. Okay, and C is compound. Okay, for compound DC motor, we have a series field resistance connected in series with the armature. Okay, and then the last one is the series DC motor, where armature and field is connected in series. Okay, so now we want to apply a Kirchhoff voltage law, KVL equation for the armature circuit. Okay, we apply KVL here, 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 and here. Okay, we go to the figure A first. Okay, KVL in armature given by, okay, given by minus VT, okay, plus IA RA plus EA equal to 0. Okay, from here we get EA. EA equal to VT minus IA RA. Okay, this is for the figure A. For figure B, shunt a separately excited DC motor. Okay, minus VT, okay, plus IA RA equal plus EA equal to 0. So EA equal to VT minus IA RA. Okay, figure C. Okay, figure C, minus VT, okay, plus IA, but here we have a RA and RF. Okay, so RA plus RF. RF here is not a shunt resistant, field resistant. Okay, this is a series shunt. Okay, plus EA equal to 0. So we have EA equal to VT minus IA RA plus F. Okay, and the last one is series DC motor. Okay, minus VT plus IA RA plus EA equal to 0. So EA equal to VT minus IA RA. Okay, from these four equations, A, B, C, and D. Okay, we can derive, okay, or we can conclude that, okay, for DC motor, EA equal to VT minus IA times resistance. Okay. Okay. Why I write here as a R? Because it's depend on the types of DC motor. Okay. Because in compound DC motor, R is equal to RA plus RF. Okay. Now, okay, we have, okay, I write equation again. EA equal to VT minus IA R. And then EA is directly proportional to K flux omega. Omega is angular speed. Angular speed unit is RPS, radian per second. Okay, and we have, or we can write the equation in terms of RPM, which is we have omega equal to 2 pi n over 60. N is speed in revolution per minute. Okay, before this, I have mentioned about the losses in DC motor. Okay, now I want to draw to you the power flow diagram of DC motor. Okay, so we have, if you still remember, okay, here we have a P in, okay, and then we have a P out. Okay, along this line is the losses. Okay, first we have a copper loss. We have a 2 copper loss, which is a PCA and PCF. And then we have a P converter. Okay, before it's convert to mechanical, we have a P converter, and then we have here is P mu or mechanical losses. We have a friction and windage, okay, stray losses, okay, or we can call it the mechanical P losses. Okay, for Assalamualaikum and a good day to all. Okay, today I will teach on how to start a DC motor. Okay, the starting of DC motor is somewhat different from the starting of all other types of electrical motors. This difference is credited to the fact that a DC motor, unlike other types of motor, has a very high starting current that has the potential of damaging the internal circuits of the DC motor if not restricted to some limited value. So this limitation to the starting current of DC motor is broke about by means of the starter. Thus, the distinguishing fact about the starting methods of DC motor is that it is facilitated by means of a starter, okay, or rather a device containing a variable resistance connected in series to the armature winding so as to limit the starting current of DC motor to a desired optimum value, taking into consideration the safety aspect of the motor. Okay, why does a DC motor have such a high starting current? So, okay, the basic operational voltage equation of DC motor is given by V equal to A plus IA RA. Okay, so from this equation, IA equal to V minus EA divided by RA. Okay, V is the terminal voltage and EA is the back EMF voltage. Okay, now when the motor is at rest, obviously the back EMF equal to 0. Why? Because EA equal to K flux omega, and the omega is the angular speed at starting. Okay, at starting omega equal to 0. So EA also equal to 0. So okay, so what happened here? So IA equal to V over RA. So starting current depends on terminal voltage and armature resistance. Okay, in practical DC machines, armature resistance is basically very low. Okay, generally about 0.5 ohm. Therefore, a large current flows through the armature during starting. And then this current is large enough to damage the armature circuit. Okay, let's say V equal to 220 volt. Okay, 220 volt divided by 0.5. So you will get high current here. Okay. Okay. Okay, due to this excessive starting current, the fuses may blow out and the armature winding or commutator brush arrangement may get damaged. And the very high starting torque will be produced. Okay, why? Because torque equal to K flux IA. So if you want to calculate the starting torque, you need to use a starting current. Okay. So, and this high starting torque may cause huge centrifugal force, which may throw off the armature winding. And then other loads connected to the same source may experience a dip in the terminal voltage. Okay. And a large DC motor will pick up speed rather slowly due to its large rotor inertia. Hence, building up the back EMF slowly, causing the level of high starting current maintained for quite some time. This may cause severe damage. Okay, to avoid this, a suitable DC motor starter must be used. Very small DC motors, however, may be started directly by connecting them to the supply with the help of a contactor or a switch. And it does not result in any harm because the gathers speed quickly due to small rotor inertia. In this case, the large starting current will die down quickly because of the fast rise in the back EMF. Okay. Okay, to avoid the above dangers while starting a DC motor, it is necessary to limit the starting current. So, a DC motor is started by using a starter. Okay, so the starter is used to limit the starting current. There are various types of DC motor starter, okay, such as we have a 3-point starter, 4-point starter, no load release coil starter, thyristor control starter, and etc. And then the basic concept behind every DC motor starter is adding external resistance to the armature winding during starter. So we add additional resistance in series with the armature resistor. Okay. Okay, this is the 3-point starter. Okay, the internal wiring of a 3-point starter is shown in this figure. Okay, when the connected DC motor is to be started, the lever is turned gradually. Okay, this is the lever. So the lever is turned gradually to the right. Okay, from left to the right. When the lever touch point 1, okay, this is the point 1, the field winding gets directly connected across the supply, and the armature winding gets connected with resistances R1 to R5 in series. We have a R1, R2, R3, and R4 and R5 connected in series. And during starting, full resistance is added in series with the armature circuit. Okay. Then, as the lever is moved further, the resistance is gradually cut off from the armature circuit. Now, as the lever reaches to 0.6, okay, 0.6, this is the 0.65 and this point run. Okay, all the resistance is cut off from the armature circuit and armature gets directly connected across the supply. Okay, this is a shunt motor. Okay, you have a armature circuit here and then you have a field circuit here. This is the terminal voltage. Okay, the electromagnetic no voltage coil. Okay, this is the no voltage coil holds the lever at this position, and then this electromagnetic release the lever when there is no supply voltage. Okay, it can be seen that when the arm is moved from the position 1 to the last position, okay, the starter resistance gets added in series with the field winding, okay, and then it is also connected with the field winding. And then, but as the value of starter resistance is very small as compared to the shunt resistance, the decrease in shunt field current may be negligible. Okay. However, to overcome this drawback, a brass or copper arc may be employed within a 3-point starter, which makes a connection between the moving arm and the field winding. Okay. And then when the motor is overloaded beyond a predefined value, overcurrent release electromagnetic. Okay, release the electromagnetic. Okay, gets activated, which short circuits electromagnetic and hence release the lever and the motor is turned off. Okay. This is for the 3-point starter. And then we have a 4-point starter. Okay. The main difference between a 3-point starter and a point starter is that the no voltage coil is not connected in series with the field coil. No voltage coil. This is no voltage coil. And then this is the this is a field winding. Okay, it is not connected in series compared to the 3-point starter. And then the field winding gets directly connected to the supply. Okay. Okay, the low voltage coil is connected with a current limiting resistance RH. We have the RH here. Okay, this arrangement ensures that any change of current in the shunt field does not affect the current through hold-on coil. Okay. And then this means electromagnetic pull of the hold-on coil will always be sufficient so that the spring does not unnecessarily restore the lever to the off position. A 4-point starter is used where the field current is to be adjusted by means of a field rheostat for the purpose of operating the motor above rated speed by reducing the field current. Okay, it means that if you want to control the speed by flux control method, we can use this starter. Okay. Okay, next we have a thyristor motor starter. Means that we control the armature current by this chopper. Okay, we connect the terminal of the DC motor with the armature chopper. Okay, and then the last one is the DC series motor starter. Okay, this is the very basic connection of the DC series motor starter. Okay, this is the series motor DC motor, and we have this rheostat, or we have this starter to control the starting current. Okay, the start arm is simply moved towards the right to start the motor. We have a start arm here, and we can move the start arm to 0.1, 0.2, 0.3 until 0.5. Thus, maximum resistance is connected in series with the armature during starting, and then gradually decrease as the start arm moves towards right. Okay, the starter is sometimes also called as a 2-point starter. And then the no load release coil holds the start arm to the run position and leave it when the voltage is lost. Okay, thank you. Okay, I have skipped several slides, and I just go to this example 1. Okay, you can find this example 1 in tutorial question number 1. Okay, before we solve this question, okay, let me refresh about this equation. Okay, we have EA equal to VT minus IAR, and this R either RA or RA plus RF series. It depends on the types of this motor. And then we have equation where the EA is directly proportional to the speed. Okay, and then omega is angular speed in revolution per second. Okay, or radian per second. And we have this equation we use to get the speed in RPM, where we have omega equal to 2 pi n over 660. And then we have another relationship between torque and armature current, where torque is directly proportional to armature current. Torque is equal to K flux IA, and K is the machine constant. Okay, and flux is flux. Okay, for the same motor, the machine constant is same. And if we change the motor, okay, the K may be differ. Okay, so okay, you try to solve this example. Okay, first calculate the rated torque, starting torque, and starting current at full load voltage. Okay. How to calculate? Okay. First is the rated torque. We know that we have the equation between torque and IA. So torque equal to K flux IA. So K flux given by 3 and IA is 5. So here we get torque equal to 15 Newton meter. Okay. The next is the starting torque. Okay. How to calculate the starting torque? So we also can use this equation, torque equal to K flux IA. So but here, how to calculate the starting current? Okay. So we have EA equal to VT minus IARA, and we have E equal to K flux omega equal to VT minus IARA. So at starting, so omega equal to 0. So from this equation, we have IA equal to VT over RA. This is a starting current. So IA equal to VT is 600 volt and RA is 2. So we get a 300 ampere. Okay, we cannot use the IA equal to 5 ampere because this is a rated current. Okay, this is the rated current and this is the starting current. So starting torque equal to 300 times K flux 3. So we get 900 Newton meter.